Hi guys, welcome to Electronics to the Point. In this video, we shall see the basic signals involving in applications of signals and systems. Actually, why should we know about these signals? Because we have to apply some different types of applications in signals, that is time shifting, time delay, time scaling, time reversal operations, so that the signals get transmitted over transmitter. So in physical system we have delays in our transmission. So and not only delays, the compression of signals and the expansion of signals because of that noise getting involved into them. So what we do is, first, in studying signals and systems, first we will see the basic signals involving in the study of these signals and systems. First, coming to the basic rectangular pulse. Rectangular pulse is nothing but a symmetric pulse which is even sorry a symmetric pulse about the axis. Okay, this is the time axis and this is the value axis, where we represent the amplitude of this signal. Let us consider this as 1, and this interval be minus t by 2 to t by 2, because we know that for any signal the period is from 0 to t, a full cycle, minus t by 2 to t by 2 or 0 to t. We can consider any for any interval, but why we are considering this symmetric interval? Because this symmetricity of the signals will yield an very fast and effective results in our signals and systems. So we have considered the symmetric pulse, that is rectangular pulse over here, and throughout the signal systems we try to convert the signal into symmetric pulse or symmetric signals, so that the evaluation get easier. Now how we can represent this rectangular pulse? See, the value axis 1, where f of t, where its value is 1 for values minus t by 2 less than t less than plus t by 2. See, this is time axis, where the time between minus t by 2 t by 2 is value axis 1, and 0 where elsewhere beyond this interval the value is 0, right? So we are representing this as else. Okay, now let us come to the next signal, that is triangular pulse. We may face some problem in sketching the triangular pulse and obtaining its mathematical equation. From this video I'll clear the problem regarding this mathematical statement. Okay, let us consider this triangle which is symmetric about the origin, and minus t to t, let the interval be. This is the time axis. So how to get the mathematical expression out of this triangular pulse? See, in the triangular pulse, this is let us consider this be two straight lines. See, these are looking like straight lines, right? See, this let us consider this is a straight line which is passing through origin. This equation will be y equal to mx, right? M is nothing but slope, x is the this time axis, this is the y. See, now let us see, consider this triangular pulse as a straight line, but with some change in this value, where this x-axis time axis value got changed for these two different straight lines. Now for this straight line, let us consider this minus t to 1, this value be, this straight line be y equal to mx plus c. Okay, here what is y? Y of t is equal to slope m into value axis t plus this constant c. Okay, how to find the slope of this straight line? Now if we see this minus t, this value is nothing but x-axis value, so minus t comma 0, we can write this value as minus t comma 0, and this one value can be written as 0 comma 1, as this is a y value, axis value, x-axis value is 0 over here, and this one. Now how to find the slope? Slope m, see, slope m is equal to, we know from the formula of slope, y2 minus y1 by x2 minus x1, from these coordinates. Y2 will be the final values, this is the initial value. See, this is initial. In the signals and system, we considered a signal from left to right, okay, from left to right. So this is starting point of the signal, so initial, and this will be the final, as we are considering the slope between minus t to 1. Okay, now what we have to do is finding the slope. M is equal to y2 minus y1. What is y2? It's 1. Y1, what is y1? It's 0, minus 0 by x2. What is the x2? 0, minus of, what is the x1? Minus t, minus of minus t. So slope m is equal to 1 by t. Now how can we represent this? See, this is the triangular pulse we have considered. Its slope m is equal to plus 1 by t. Okay, from minus t to this value 1, this is the origin value 0. Similarly, how we can find this value of this dropping slope? See, we can see from at the value of 0 it is dropping, right? So the value obviously will be here plus 1 by t, means it will be the minus 1 by t. We can find this too. How? We consider this value as 1 comma 0, and this is plus t, right? So t comma 0. Now as we are considering from left to right, so this will be the starting value and this will be the final value. So what will be a slope? M is equal to, what is the y2 here? 0, 0, sorry, this value is 0 comma 1. X and y value is 1, x value is 0 over here. So y2 value 0, y1 value 1, so 0 minus 1 by x2 is t minus x1 is 0, so m equal to minus 1 by t. This will be the slope. So we have got the slopes of these two straight lines. Now how to represent the value of this signal triangular pulse in mathematical form? See, what we have said, these are like straight lines, right? So from f of t is equal to, that is slope m is from minus t to 0, the slope is 1 by t into t plus the constant c, where from minus t less than 0, right? Now minus 1 by t into t plus c, where from 0 less than t less than plus t. This will be the mathematical statement of this triangular pulse. This is how we solve this triangular pulse mathematically. The first thing we have to remember is consider this in the form of straight lines. See, as this is not passing through origin, we can consider this as a straight line with constant y mx plus c. Okay, from this we have to find the slope. We know now how to find the slope from minus t to 0, that is from at 0 its value is 1, right? So how we have found this? From the slope equations we know. See, this is how we get the this triangular pulse. Next coming to the important signals, we use this triangular pulse and rectangular pulse in this representation of signals and systems. And now secondly, we'll go for the sinusoidal signals. These are the heart of signals and systems. Why do we consider sinusoidal signals for the evaluation of any signals in the subjects of signals and systems? Because sine and cos are the orthogonal signals, so we consider these two signals in the evaluation of any signals and systems. Okay, now coming to the sine signal. First basic signal is sine signal. Let us consider this as sine kt. Simultaneously we can consider the cos signal, cos kt. See how to draw the diagram of this sine and cos, this graphical sketching, because see the values where sine value gets 0 and cos value gets 0 are called zero crossovers. Okay, where the zero crossovers are present, this sine graph will be oscillating to and fro in their zero crossovers. Okay, where the value of sine will be 0, sine 0, sine pi, sine 2 pi, and so on. So we have represented that sine kt. We can draw like this. See, these are periodic signals. They repeat from minus infinity to plus infinity. See, starting from somewhere minus infinity, this is the sine signal, and this gets tends to plus infinity. See why this sine signal is starting from, if we consider this right sided signal of this sine, why this is starting at 0 point? Because sine zero crossover is at the value of 0. The sine signal has the zero crossovers, 0 at pi, sine pi is 0, so this will be the next period, and for 2 pi again one crossover. So we at crossovers this sine value changes or oscillates to and fro. Let us enter this 1 1. Okay, now how can we say this sine representation of sine in the mathematical form? See, where does the zero crossovers occur? Sine is periodic with its zero crossovers, so zero crossover of sine t is equal to k pi, right? For a value of k equal to 0, it's 0. For a value of k equal to 1, see k equal to 0, 1, 2, so on. For a value of 2 pi, sine 2 pi value is 0, 0, pi, 2 pi, 3 pi, 4 pi, and so on. Now coming to the cos signal, cos kt, where the value of cos will be 0. At cos value is 0 when the value of it is pi by 2. Cos pi by 2 is 0, cos 3 pi by 2 is 0, likewise cos 5 pi by 2 is 0. So how we can represent this zero crossovers? See, cos signal, we said that it has zero crossovers only at pi by 2, right? This is pi by 2, 3 pi by 2, and this is minus pi by 2, 0, minus 3 pi by 2, so on, so on. This is the representation of sine. This is time axis, this is the value axis. Now see, where the cos value is 0 is called zero crossover. We can represent the zero crossover of cos signal is, or cosine signal is, 2k plus 1 into pi by 2, right? For value of k equal to 0, k equal to 0, 2 into 0 is 0 and it's pi by 2, right? We got pi by 2 value. For value of k equal to 1, 2 into 1 is 2, 2 plus 1 is 3, 3 pi by 2. 3 pi by 2 has a 0 crossover. See, this is how we can represent the periodic cos signal through its 0 crossovers, right? K value from 0, 1, 2, so on. Okay, this is how we can represent the sine and cos signals with their 0 crossovers in single statement. Okay, sine has 0 crossover k pi, cosine signal has 0 crossover 2k plus 1 into pi by 2. Okay, now we will go for the exponential signals. Why do we go for exponential signals in the signals and systems? Exponential signal or the Euler signal is the best possible way of representing any signal. See how, why we have taken this sine and cos in the representation of signals and systems? Because they are orthogonal to each other and they can form complete sets. So we cannot get any other individual independent signal getting involved into this or set of sine and cos, because sine, cos are even and odd signals. Any set of thing in this world can have even and odd, but other than even or odd we cannot get anything, and this orthogonality will be discussed in our further videos. Now basic we have to remember is sine and cos are periodic signals and these are orthogonal to each other, so we consider this in the signals and systems. Now why we have to consider the exponential signals or Euler signal? E power jt, Euler signal or function. We know e power jt can be represented in its rectangular form, in polar form as cos t plus j sin t. This is how we represent e power jt, cos t plus j sin t. So we consider this Euler signal for representing any signal in the signals and systems, because two sine and cos signals, both the orthogonal signals are found simultaneously at a time, so we are considering the Euler signal. See, now consider the exponential signals involving in this signal systems and how can we represent it? E power plus at, e power plus at, exponential plus, so exponential increasing function. How we can represent? Let t equal to minus infinity, e power minus infinity is equal to, putting t equal to minus infinity, we can get e power minus infinity is equal to 0, in the sense at t equal to some point of time minus infinity where exponential value is 0, it is starting from a 0 value somewhere from minus infinity. If we put t equal to 0, e power 0, at t equal to 0, e power 0 it will be, and the value will be 1. At t equal to plus infinity, e power plus infinity is equal to some value infinity. Okay, remembering this, let us plot the exponentially increasing function. See how we can say it is exponentially increasing from this. At t equal to minus infinity, we found that the value is 0 at somewhere minus infinity, and we cannot go to minus infinity, so let us see just like this, and the value increasing at t equal to 0 the value is 1, and at some infinity it is increasing till infinity. This is the exponentially increasing signal, e power at. Okay, now exponentially decreasing signal, second one, e power minus at will be the exponentially decreasing signal. How? At t equal to minus infinity, when we put t equal to minus infinity, we will get e power plus infinity. So the value of e power plus infinity is infinity. At t equal to 0, e power 0 will be 1. At t equal to plus infinity, the value, putting t equal to infinity, e power minus infinity is equal to some value 0. So what we can say, somewhere from minus infinity the value of exponential is infinity, and at t equal to 0 e power 0 value is 1. At t equal to infinity the value getting in 0. So how we can say, somewhere from minus infinity it is coming, and see, we can see the gradual decrease. So this is how we can plot, and we cannot find the 0 value because this is the infinity, we cannot go to infinity. So let us see, this will be the exponentially decreasing function. This is the e power minus 80 exponentially decreasing, and this is the time axis, okay, at 0. Now coming to the important signals, these are the most important part of signals and systems. See, these are unit step signal, unit step signal. Step, this can be represented as u of t. See, unit step is a non-periodic signal. It has a value of, at 0 it gets excitation, and the value changes to 1 and tends to infinity. Let us consider this one, unit step, unit, so this value be 1. U of t is the step signal. We consider unit step, so we taken 1 as its change at 0 equal to 1. How we can represent this in mathematical form? U of t is equal to, value is 1, where for t greater than 0, and the value below this 0 is 0, so 0 for t less than 0. This is the representation of unit step signal. This is the most important signal we use in the signals and systems. And second signal is unit ramp signal. What is a unit ramp signal? See, from basics of mathematics, this is a equation of straight line. Let us consider this y of t, this is the time axis. Equation of straight line, this is a straight line passing through origin. How we can write? Y of t is equal to mx, y equal to mx, the straight line passing through origin. So here how we can, this x value, y of t is equal to m into t, right? Now what is a ramp signal? A ramp signal is nothing but a signal or a straight line passing from the value 0. This will be the ramp signal, okay. Let us represent this as r of t. Now we have considered the unit ramp, right? So up to a value 1 we have to find the slope, so that unit ramp can be found. What is ramp? Actually is a value or a straight line which is traveling from origin to infinity linearly. This is a unit ramp signal. For unit ramp signal, how to represent this mathematically? We know from how to find this is straight line slope, we have to find the slope m. How to find slope? M is equal to y2 minus y1 by x2 minus x1. See, this is the one y axis value, so value axis value, so 0 comma 1, sorry, this is the at this point, and this will be the initial value, this will be the final value. So how we can find the value of this unit ramp signal? Say at this point 1 comma 1, at this point 1 comma 0, right? See, this is x and this is y value. So unit ramp, how to find the slope? Y from 0 to this point we are finding the slope, right? So y2 minus y1. What is the value of y2? This is the final value, this is the initial value. At origin the coordinate is 0 comma 0, so y2 1 minus y1 0 by x2 1 minus 0, slope is equal to 1. So as this is passing through straight line, so how we can be represent? Now y of t we can write as r of t is equal to slope m is 1 into mx. X is the x coordinate value axis. Now it is shift, it is represented as time axis here, so into t, y is equal to m into x is nothing but r of t is equal to slope 1 into time t. This is how we can represent mathematically. So r of t is equal to t for value t greater than 0, 0 where for t less than 0. This is how we can represent the unit ramp signal. Okay, and this is unit ramp signal can be obtained by taking the straight line, considering the straight line passing through origin. This, let this be y and this be x. As we are considering this in signal systems, let this be time axis and this be value axis y of t. When multiplied by an unit step signal, which is from 0, starting from 0, so by multiplying this unit step signal with unit ramp signal, this has only value after 0. So the value which is having after 0 will be multiplied. 1 into 1 is 1 and this value is 1, but here value is 0, so 1 into 0 is 0. So that by multiplying unit this straight line passing through origin with an unit step signal, we can get a unit ramp signal. Okay, this is r of t, this is the unit ramp signal. Okay, this is how we can represent r of t equal to t for t greater than 0 and 0 for t less than 0. This is a unit ramp signal. The third signal, which is the most important signal in the evaluation of signals and in the signals and systems, that is impulse signal. Impulse, what is meant by impulse in general English terms? Impulse is nothing but a sudden reaction or a sudden jolt given to something which causes the maximum damage. That is the impulse signal. See how we can represent this impulse. This representation of impulse is by del of t. Okay, now what is the impulse signal? Impulse is nothing but its value is 0 everywhere except at origin it has some value which is unknown to us. How we can represent this mathematically? The value is 0 elsewhere, but at origin it has some undefined value. We cannot say it infinity, but some value we can estimate it from the impulse signal. Okay, something which cannot be, we can say it infinity, but the infinite value is also defined somewhere, but we cannot, we humans cannot find the value of infinity, so we neglect that value. That's why we are considering as infinity. So what we can say is this has some finite value at 0, that is origin, but 0 elsewhere. This is how to represent the impulse. Impulse del of t is equal to some value t equal to 0 for t not equal to 0. See, t not equal to 0, that is without considering the at origin, the value of t is 0 everywhere. This is the meaning of 0 for t not equal to 0, and that is value of value axis, it is not equal to 0 for t equal to 0. See, at t is equal to 0, I said it has some value, some defined value. but we cannot find, so we consider it as infinity, but we should not represent it as infinity. Del of t is 0 for t not equal to 0, and the value is not equal to 0 for t at t equal to 0. This is how we can represent the impulse signal, and the impulse signal can be represented as area under del of t is unity. This is the most important thing to be remembered in the impulse case. The area of del of t is 1. Integration from minus infinity to plus infinity, area under del of t minus, whenever we consider integration we are considering the area del of t dt is equal to 1. This is the most important case we have to remember. These are some signals involved in signals and systems. In our next video we will see the applications of the time delay, time advancement, time reversal, time scaling properties on these signals. Thank you guys.